Next, I'm going to do is dispersion of light via prisms. Right. So you may ask that why not dispersion of light by glass tape? All right. Glass tape normally doesn't gives dispersion of light. Maybe you have done this in the lower class. All right. If time permit, I'll explain you why a glass tape does not give dispersion. Right. So now we are going to talk about dispersion. Dispersion is normally given by glass prisms and droplet of waters and all, right? So now look at here, dispersion, right? Look at here, when a light undergo a refraction is when the light goes from one medium to another medium. That is, this is a glass medium, this is the glass medium. Look at here, and this is air mediums. All right. When a light goes from air medium to glass mediums, light undergo refractions. This is done in lots of refractions. And then now when I say light, in a sense, it is a white light, visible light or white light. And we see that a white light consists of 7 colors. White light consists of 7 colors. All right. So now if I say the beam of white light, look at your white light. When a white light falls and reflect into a glass prisms. Now look at here. This is what I would like to tell you. Again, I will bring a standstill slow. Again, I will bring a standstill slow. So when I define this standstill, we say that this is constant for a given pure media and for given wavelength. So that means this is not same for all wavelength of light. This is not same for all wavelength of light. A different wavelength has different refractive index. All right. Again, I'm repeating. Different wavelength of light has different refractive index. Again, I'm repeating. Different wavelength of light has different refractive index. If I say it has a different refractive index, the bending would be different. So different refractive index undergo a different bending. Alright? If a refractive index is more, bending is more. If a refractive index is less, bending is less. So this is the reason, right? So now I'll come to this. When a white light falls on one side of a prisms, it undergo a refractions. Alright? And all the 7 colors, alright? All the light of a different color undergo a refraction with a different angle. Alright? So look at here, this is a red. Undergo a lease. This is a lease. And this is a violet, which undergo moss. And all other colors lie between these two colors, right? So I say, when a red light goes into glass mediums, alright, the refractive index of red light is going to be less or least. So therefore refraction is going to be, the bending is going to be least. And the refractive index of a violet is going to be maximums. Therefore the bending is going to be maximums. Alright. So this is the reason, right? This is the reasons why light splits when a light goes into prism. Why? Because the light with different colors reflects the different angles, so splitting take place. Therefore, splitting take place. Again, look at here. When a light comes out from this, alright, again, the red color undergo a least bending, and violet color undergo a maximum bending. It further separate. You see a splitting take place when a light enters through one first surface, and the further splitting take place when a light pass through a second, a side of a prism. So therefore, when a light emerges out from a second side, light appears 7 colors. That red, orange, yellow, and up to violet. So this is what we call as dispersion of light. This is what we call as dispersion of light. So why dispersion occurs? Because of the fact that refractions or refractive index is also defined by wavelength of light. Alright. So therefore, I define a dispersion of light. It is a phenomenon of splitting of light into its component. So this is what we talk about the definition of dispersion of light. This is what we define as dispersion of light. Look at here. So this is what we have. And look at here. And then when it comes out, look at here. When you look at this, you find a continuous distribution of a light range from red to white. You see a continuous change of light, continuous change of colors, right? Continuous change of wavelength. Alright, so therefore, this pattern of color is what we call as visible spectrums. Alright, so this pattern of a color is what we call as visible spectrums. And we know the wavelength of a visible spectrum goes from 700 nanometer to 400 nanometers. This is what we call as visible spectrums. Visible spectrums of light. Visible spectrum of light. Alright. And now look at here. This is a visible spectrum of light. And now you know this also comes under electromagnetic wave, which I told you long back. And when you talk about electromagnetic wave, the spectrums goes from gamma radiation to gamma to a long radio waves, long radio wave, and in this long range of electromagnetic spectrums, the visible spectrum is the visible spectrum comes under this long spectrums of electromagnetic waves. So this is the point, right? Now look at here. So this is what we define as dispersions by prisms. This is now look at here. When you look at the history, right? Long back, maybe 3,300 years, 400 years back, people thought two things, right? They say that maybe a prism creates 7 different colors, a beautiful 7 different colors. And some say that no, it is not a prism that creates, it is a light which has all these 7 colors, and this is a prism one which splits a light into 7 different colors. Alright, and finally it was Isaac Newton who performed one very simple experiment which proves that visible light has a 7 different color, or visible light has a 7 different wavelengths. Alright, this is what we have. This is the Isaac Newton who's proved that. Look at it, this is a very simple proof. I think this is done in class 10. What he did is very simple, right? A light undergoing dispersions by first prisms, and then what he did is he collect all the all the different light and merged. So this prism. The purpose of this prism is a splitting, right? Splitting, and by splitting we get a 7 color. And now, if I put this prism in inverted, it will this prism does the opposite of earlier prism. So therefore, this merge, all right, recombination, these recombination of all 7 colors, all right, if I put this inverted, recombination take place, and finally we found that a white color. Finally we found a white color. We send a white color, we get white color by combining all 7 colors. By combining all 7 colors. This ensures that it is not a prism that creates beautiful colors. It is the light which has 7 colors and which we call as visible spectrums, and it is a prism that splits light into 7 different colors, and this is what we call as dispersion. Alright, this is what we have. And now next what I'm going to do is I'm going to do a few natural phenomena which occurs in nature due to dispersions, refractions, reflections. So the first such a phenomenon is what we call as a rainbow. Alright, rainbow. Let's say the rainbow. I see rainbow. All right, this could be really interesting. Like say rainbow. All right. So we normally see a rainbow just after rain or during a rain, right? All right. We never see a rainbow during a completely clear sky. All right. Should have some rain. All right. So now, therefore, whenever we talk about rainbow, there must be so many droplets of water in a space or in a sky. All right. So now, let me first give you our conditions. Right. You don't see rainbow everywhere. Right. You have to have some condition to satisfy in order to see rainbow. So what I'm going to tell you is, let's say you are seeing at one part of Earth, that is, let's say this is west horizons. West horizons. You are seeing at the west horizons. Sun is, this is the sun. I'm sorry. Sun should be at one part of sky. This is west horizons. And then I say, where should be raindrops? Where should be raindrops? Where should be raindrops? Raindrop should be at the other part of a sky. Let's say it is going to be a east horizons. This is east horizons. So raindrops should be at east horizons. Now the point is where observer should be. Observer should be here. Observer should be here such that the back of the observer should be towards sun, and you should face towards raindrops. So this is the minimum condition has to be satisfied in order to see rainbow. So very simple. Sun should be here, rain should be at the other side of the sky, and you should be in between sun and raindrops, and looking at the raindrop, not looking at sun. All right. Now I would like to discuss what things are taking place. All right. Say rainbow is again due to dispersions. Dispersions of light taking place in a raindrop, water droplets. Dispersions of light taking place in a water. Dispersions. I just write here. Dispersions of light taking place in water droplets. Water droplets. So this is water droplet. I'll explain you. This is a water droplet, and here is a sunlight. When a sunlight falls on the water droplet, and sunlight undergo dispersions. Sunlight undergo refractions, that is what we call dispersion. Why? Because splitting of light takes place. Alright? This is going to be a least banding, and this is going to be a maximum banding. This is a red, and this is going to be a violet. Now next thing is that this is angle of respect to other surface. This is angle with respect to other surface. Now look at here. If this angle of incidence is more than, let's say, 48 degree. So 48 degree is critical angle for water. If this angle and if that angle is more than 48 degree, and instead of refraction, it undergo total internal reflections. It undergo total internal reflections. And then when a light comes out from the same phase of raindrop, it further undergo reflections. Alright. And it comes out, this is a violet, this is a red. It is such that, look at here, it is such that the angle between violet and incident sunlight is 40 degree, angle between red and incident sunlight is 42 degree. This is what exactly taking place in every droplets of rains. I have shown you only single drops, and this is what exactly taking place in every drops of waters in a sky. This is what I have shown you in every drop. Now look at here, since we have so many drops of water in the sky, this is what we exactly find. This is what exactly we find. So, therefore, this is what exactly we find. This is a raindrop, alright, and this is normally what we call as a primary rainbow. Primary rainbow. So, primary rainbow consists of two refractions and one internal reflection. Two refractions consists of two refractions and one total internal reflections. Look at here, this is what we have. Again, I'm going to explain you. This is what we have. This is the observer. Observing, this is what I say, this is the sun. Conditions are satisfied. Sun coming from west horizons and the drops are at the east horizons. You are lying between these two. And look at here, the light from this first drop, this is a violet and this is a red, and this is for a second drop, this is the violet and this is the red. Now look at here, to our eye, we could able to catch the red of a first drop and violet of a second drop. So this is going to be red. Alright, so this is red, 42 degree. So therefore you could observe a rainbow within this range, 40 degree to 42 degree. All other colors are lying between these two. So therefore when you observe a primary rainbow, we see normally first red and then followed by indigo and all, then finally we see violet. This is what we have. Alright, this is, so the angle should be from 40 degree to 42 degree. Alright, so angle with respect to what? With respect to incident sunlight. Incident sunlight. So if you see here and along a range of angle 40 to 42, you could see rainbow. This is a primary rainbow. This is a primary rainbow. So I just say the red of first light of first drop enters into your eye with angle 42 degree, and then violet of a second drop enter into your eye with angle 40 degree, and then all other colors align with this two, and this is how you could see a primary rainbow. And this is what I have. This is a little better. Alright. So you have observed is here sun is, this is sun at the opposite side, and you could see like this. Now let's talk about secondary rainbow. Secondary rainbow. Secondary rainbow consists of again the two refractions and two internal reflections. Total internal reflections. Internal reflections. This is what we have. So again, look at here. Little different from a primary rainbow. Let's say this is the first drop, this is the second drop. Sun, this is the sunlight approaching droplets of water, and this undergo two total internal reflections. These are the two total internal reflections. These are the two total internal reflections. And this is the first reflections. This is the second reflections. First refractions, second refractions, and then the violet of first raindrops enter through eye with the angle, let's say, of 53 degree, and the red of a second drops enter into your eye with angle 50 degree. All other colors lying between these two. All right. So therefore, this is what we have. For therefore, in case of a secondary rainbow, we find violet at top, and red at bottom. And one more information I would like to tell you is, for secondary rainbow is at a little higher angle, that is from 50 to 53. So there it could be something like, first you will find a primary rainbow, and little higher to a primary rainbow you find secondary rainbow. Alright, you find a continuous change of colors, right? So this is for a primary rainbow, red to violet, and then you find a red to violet. So this is what you see in case of a secondary rainbow. Here I have examples, right? This is what we have. So I have a primary rainbow and I have a secondary rainbow. So you could see that secondary rainbow is little higher. However, secondary rainbow is little faded, right? The visibility is little less while it undergo two total internal reflections. Because of two total internal reflections, some light may decreases, intensity of light decreases because of the fact that it undergo two total internal reflections. So this is the nice diagrams. So I have this consists of both total internal, both secondary as well as primary rainbow. This is primary rainbow, this is secondary rainbow, and I have few more. This is what I have. This is for secondary rainbow. The secondary, the two total internal reflection taking place in one droplet of water. This is one total internal reflection taking place. This is what we have. This is a primary rainbow. This is a secondary rainbow. Now we would ask, maybe this may be having this kind of portions may be helping to every students, saying that why rainbow appears bow in shape. Why shape looks like this? All right. And maybe the detailed answer is beyond our scope. Why? Because you need more geometry. All right. You need more mathematics. However, the simple answer is that when you observe, when you see a rainbow, all right, it is the only that droplets. These are all droplets. These all droplets, and you are not at, you are at the focus. You are at the focus of this ball, right? This ball, all right. So therefore, all other colors, all other side, you know, from here to that side, the conditions are satisfied. What conditions? Angle should be from 40 to 42, all right. And such a curve appears bow in shape, right? I'll give you one more diagrams. So this is what we have. This is more visible, right? So this is that side, and you could see this is the sun coming from light. And look at here. So this satisfies. This is a bow in shape. Why bow in shape? Every raindrops, every rainbow satisfied what conditions? That angle from 40 to 42 degree, right? So therefore, this is something like a cone. Alright, this is something like a cone you have. So I have a cone like this. I have a cone like this, and you see the you would find the focus of a cone. Alright, you could see the focus of this is going to be the last corner, right, of a cone, and all the light comes to that and point with the same angle, so that satisfies rainbow. Alright, this is all about rainbow. Now next I would like to discuss is scattering of light. Next we are going to discuss is the scattering of light. Scattering of light. So when a light enters into our atmosphere, light undergoes scatterings. And the scattering of lights is defined by the way the light undergoes scattering is defined by a size of particle. Depending on the size of particles, light undergo a different kinds of scatterings. Alright, so depending on the size of particles, so we divide this into a two. First scattering, if the size of a particle is very small compared to a wavelength, we say that the scattering is what we call as a Rayleigh scatterings. This is what we call as a Rayleigh scatterings. So when we talk about Rayleigh scatterings, alright, it says that the amount of scatterings is inversely proportional to 4th power of wavelengths. This is what we have in case of Rayleigh scatterings. When we talk about Rayleigh scatterings, the amount of scatterings is inversely proportional to 4th power of wavelength. That means if a wavelength is smaller, scattering is going to be more. If a wavelength is longer, scattering is going to be less. So this is what we have in case of Rayleigh scatterings. And then I would say that A is very, very small compared to lambda. That means atmospheric part. That means the air, the molecules, right? Atmospheric molecules, that is oxygen molecules and nitrogen molecules. Those molecules are very, very small compared to a wavelength of lights. Therefore, the Rayleigh scattering takes place. So therefore, I say this is the atmosphere. I just say this is the sunlight. Sunlight enters through our atmospheres. So what you see is you see the maximum scattering of normally the blue light scatters maximums. All right. Therefore, you would see a bluish sky. Why sky appears blue or bluish means why? Because the wavelength of blue is less compared to all other light, all other colors. Therefore, the maximum scattering is normally the blue normally takes the maximum scatterings, and you find a blue color every day in our space, everywhere in the sky. Therefore, sky appears blue. All right. And then you see the violet. So right. So yes, violet scatters more. However, to our eye, the blue is sensitivity toward the blue is much more than violet. So this is the reason. All right. Then again, we have. And again we have why the sun appears reddish during a sunset. Again, this can be explained by this. When during a sunset and during a sunrise time, the sunlight has to travel longer distance in the atmosphere. So therefore, the blue colors and all the shorter wavelengths already scatters, and it is the red which could enter into our eye. You could see here the red that is entering into your eye. So therefore, the sun appears reddish. And here also we have given you this. Since you could see more blue colors entering into your eye, so therefore you could see a bluish color. So this is all because of Rayleigh scatterings. This is all because of Rayleigh scatterings. All right. And now look at here. So this is what we said: blue skies and the red sunset time is all because of Rayleigh scatterings. All because of Rayleigh scatterings. What kind of scattering it is that the scattering particle is very, very small compared to wavelength of light. Now next is what about if a particle is much bigger than wavelength? If a particle is much bigger than wavelength, then instead of Rayleigh scatterings, this scattering, MIE scattering take place. And this scattering says that amount of scattering is almost equal, right? This says that amount of scattering is almost equal to all wavelengths. Amount of scattering is equal to all wavelengths. So therefore what you see is you see white. You could see white. So this is what we see, right? When a sunlight scatters from a droplet of waters in the atmosphere, since the droplet of water is so big compared to a wavelength of light, and MIE scattering take place, therefore the clouds normally appears white. So this is what we have. All right, this is what we have. Therefore, if the scattering object is big, then amount of scatterings is almost equal for all the wavelengths. So therefore, what we see is we see white lights. All right. So this, therefore, what we can know today is why sky appears blues, why sun appears reddish when during a sunset and sunrise time. Is all because of Rayleigh scatterings. Why clouds appears white, is all because of MIE scatterings. Why? Because the droplet of water is big compared to, and normally whenever you see, right, we could get a light without actually sun in a room. Why? Because we get a scattered light, and that scattered lights are normally white light. Why? Because we get light from an object which are pretty big compared to a wavelength of light. All right. So therefore, this is what we have. All right. So with this, we come to an end of reflections. Now next class, I'm going to do optical instruments, that is telescope and microscope. Okay, thank you.